Good morning, everyone. My name is Harsh, and I'm going to present my master's thesis work on hierarchical reinforcement learning for aerial vehicles. And this was advised by Dr. Vijay Kumar. So I'll just start off with some of the background. One of the hallmarks of human intelligence is to complete a task, for instance, just navigating across an indoor environment, like an office environment or a building, using skills. These skills just include running, walking straight, opening the door, or even turning right along a corridor. And each of these skills are a byproduct of millions of muscle commands. Now, we don't really consciously optimize for these motor commands, and these skills are actually learned naturally over a lifetime. This setup or hierarchy is not new, and a lot of our robotic systems already have this for many task and motion planning problems. We have seen this very commonly in autonomous vehicles, ground robots, and robotic arms. The typical pipeline over here is to first construct skills in the form of motion primitives that are handcrafted or engineered or sampled. Then there's a higher level planner that basically composes these primitives in sequence to complete that particular task. This has also been some of the focus of prior work and has been an emerging interest for aerial vehicles as well. In this case, the primitives are constructed by sampling states such as positions, orientations, and velocities for the quad order, and we optimize trajectories amongst any two sample states. On the higher level, a search-based motion planner would then select a sequence of these primitives based on some heuristic for a task, for instance, navigation, as shown in the second GIF over here. However, the quality of the plans are constrained due to the two sources. One of them is that on the higher level planning side, heuristics for the search-based task planning can be quite difficult to design. And even suboptimal heuristics can lead to suboptimal trajectories. Motion plans themselves are constrained also by the quality of motion primitives. So if the coverage of the sample states initially to construct these motion primitives is insufficient, this would generally result in suboptimal trajectories for the task. If we want to sample densely, this would result in higher quality paths, but this also comes at the high cost of higher compute time for the higher level motion planner. So there's a trade-off over here. This was the focus of my work, essentially, where the objective over here is to investigate whether learning can help in in devising these higher level task plans, as well as whether we can use learning to learn these primitives from data. More specifically, we want to use reinforcement learning to learn a good high level task policy over a dense set of motion primitives to offset this problem of engineering heuristics for a given task, as well as reducing computing time so that we can enable online planning. On the lower level control side, we want to investigate how we can acquire these skills in the form of a single goal condition policy from offline data. And the brief objective over here is we would learn a policy which would essentially take like the current state and the goal state, and this would be a neural network, and the policy commands would be for the aerial vehicle to reach this desired goal state from the given initial state. So I'll dive right into the first part of my talk that would cover this task planning problem, and we look at this in the context of informative path planning. So in this problem setup, you can take a UAV in a search and rescue setup, and you're tasking the UAV to find an unknown number of targets or semantics in an environment, and you're giving the UAV an onboard sensing equipment such as a camera. Now, assuming that we have some a priori information that can be used to initialize this prior over targets, this could be done via satellite imagery, by investigating weakly correlated information such as damage to buildings. These initialized priors might not be fully accurate, wherein they might diverge from the true distribution of the targets or the semantics. So now, given this prior, which we only have access to, how should we plan dynamically aware UAV trajectories to detect these targets and semantics accurately? The dynamics requirement is easy to meet. We can use this by handcrafting or engineering motion primitives. But the primary challenge in this task is to design a heuristic for a planner to use the inaccurate prior to detect those semantics or targets. Now, there is an exploration and exploitation problem here. As you can see, purely exploiting this prior by using it as a ground truth would result in the aerial vehicle missing some targets or semantics. On the other hand, if we were to uniformly explore this environment, we might run out of budget before even finding those targets. So there is a additional requirement to plan trajectories that trades off between this exploration and between exploring and exploiting this prior. And we want to explore the prior so that we can search over areas where the information from the prior might be inaccurate. In this problem setup, we follow prior work. We basically follow prior work to devise these set of motion primitives, whereby goal states are sampled in a way that minimize dispersion between them for good state coverage. For an aerial vehicle, this results in forming this local motion primitive graph, as you can see in the second figure over here. The primitives then can be composed in runtime to give dynamically feasible continuous trajectories. And this has been shown in prior work as well. After this, we can use these motion primitives as a suitable action space for any deep RL algorithm, where the objective now is to just select a sequence of primitives using some neural network. And this would be a task-specific neural network. In our approach, the input, we train this policy, this high-level policy, using the asynchronous aptocritic RL algorithm, whereby the input of the policy is essentially the egocentric feature maps. As you can see on this image over here, the egocentric feature maps comprise the target or semantic beliefs over each semantic category. And these beliefs are updated by observations from the environment, for instance, the sensing module. The second feature map that we look at is a coverage map, which basically maintains an image-based log of where the aerial vehicle has been in the entire environment. And there's an obstacle map that basically represents the boundaries of the environment. Now, all of these maps are taken over multiple fields of use. And the higher fields of use have poor resolution so that we maintain the same size of the network. The policy then basically selects a valid outgoing primitive or edge based on the current pulse of the aerial vehicle. And it optimizes for a reward that is based on finding targets or semantics, covering the environment, and maximizing information gain. Some of the results of the learned policy is on the slide. So basically, you can see the resulting trajectory of the aerial vehicle when it executes this policy for a target search setup. So the top left over here depicts targets in red and the underlying ground truth distribution from which the targets are sampled from. And the second figure is basically the prior that the aerial vehicle's target occupancy map has been assigned to. And you can notice that there's a mismatch. The figure over here on the right is basically the trajectory taken by the quadrotor and the updated target occupancy map once the aerial vehicle has gone through the entire environment and executed its trajectory. So here the AV is basically initialized at this purple location, and its trajectory terminates at the red location once it exhausts its budget. We also do this for the semantic search task. And in this case, instead of finding single pixel targets, as you saw in the previous case, here we are looking at semantic categories. For instance, these could be like traffic lights in an environment, could be buildings, parks, etc. The ground truth semantic features are shown on the images on the left. The priors that we initialize the semantic beliefs with are shown in the images in the middle, and the right images are the paths that are taken by the aerial vehicle. We also show we also visualize some of these things in action. So for instance, you can see the aerial vehicle moving around the environment, detecting semantics based on the prior that is in the middle image. The detected semantics and the targets are shown in the image on the left, and the ground truth semantics and targets are shown on the image on the right. We also qualitatively benchmark the learned policies, and we use a set of baseline heuristics that are usually used in informative path planning that have been adapted with this motion primitive framework to have a fair comparison. And we show that the policy that is learned by using our method and using our a set of state space design and features, can actually improve over commonly used metrics for informative path planning, such as search efficiency, environment coverage, and information gain. We also noticed something that is really interesting. So our method, which is shown in green on the image on the right, performs consistently in cases where the prior and the true target distribution diverge. So the divergence over here is basically the KL divergence between the ground truth and the prior. So this indicates that the resulting trajectories from the learned policy actually learns to balance between the covering and the exploiting of the prior, thereby improving target search efficiency, especially in those cases where those priors might be inaccurate. We also do this benchmarking for the semantic search case. In this case, we compare it with respect to the same heuristics, and we see that we get a 3.5% over semantic search efficiency. Notably, this is a much harder task to complete, and that is why there's a smaller performance gain as compared to the target search task. With this, this brings me to the end of the first half of my presentation. So basically, where the key contributions are that we could learn a task-specific policy over motion primitives by choosing the right set of features and reward structure. And we can, whereby this task policy can also outperform heuristic-based search for a lot of these informative path planning tasks. Future work can now focus on better designing those network architectures for the policy network. This is to just better process those local observations in terms of the feature maps that were introduced earlier. Moreover, planning quality is also constrained by the choice of motion primitives, and this was observed to be true in the case of the semantic search task. Proposing an alternative to sampling-based primitives will be the focus of the second part of my talk, essentially. And the question that we want to ask over here is basically, can we learn these motion primitives just from data? In this case, primitives would be in the form of a Goel condition policy. So the inputs to the policy network would be the current state and the goal that you want the aerial vehicle to reach. And the policy would output basically a set of control commands, low-level control commands for the aerial vehicle to reach that goal state. I'll just briefly go over the current state of the art in terms of motion primitives. So essentially what happens is current methods, in a nutshell, for devising such primitives would first sample states arbitrarily, or this could be done cleverly in which was used in the previous in the first half of the presentation, where we use dispersion minimized states. And then the primitives can be constructed by optimizing for the reference trajectories between any two sample states. This procedure would give you these dynamically feasible paths between any two states. And now the objective is to simply select primitives for any high-level planner. What we are trying to do is something different here. What we want to try to do is we want to learn these skills of primitives from data. And this data would be collected by from an expert controller that would be essentially executing some that basically you can collect from some flight data that you must have used for previous tasks. And the objective is that you want to learn a policy that can reach a desired goal state from this initial state. An added advantage is that this policy would not require you to compute this intermediate reference trajectory, which is a common thing to do for a lot of these aerial vehicle control and planning tasks. And we're abstracting away the lower level control requirements to this goal condition policy so that the higher level task policy can use this low level goal condition policy directly for any downstream task. The first step towards learning this policy is to just collect flight data. For control and motion planning in aerial vehicles, differential flatness-based planning and control is a very classical approach, and we simply leverage this to collect our data. In order to do this, we first sample a data set of 250 desired goals in flat space. The flat space for essentially an aerial vehicle comprises of the positions and the yaws. Here, the goals are specified by positional offsets, which is basically, we basically constrain it to 1 meter to 2 meter radiuses around the origin, velocities up to 2.5 meters per second, and accelerations up to 5 meters per second squared, all in flat space. We then optimize a reference trajectory and then compute the desired controls to track this reference trajectory using a geometric controller, which is basis of prior work. And once we run this geometric controller on the aerial vehicle, all the states that are achieved, we'll refer to them as achieved goals. We log all of these states and the associated control commands. During the data collection phase, we have this, we also optimize for a reference trajectory for this aerial vehicle. And we want to compute a time optimal reference trajectory to ensure that we have good quality expert data. So the optimization thereby has two layers: an outer loop optimization, which basically computes, which basically optimizes for the time to complete this maneuver to the desired goal, as well as an inner loop optimization, which computes the minimum jerk reference trajectory based on the time that comes from, based on the time input from the outer optimization loop. In a nutshell, what we're trying to do is we want to optimize for the quickest maneuver time for this aerial vehicle, such that the constraints in the lower level reference trajectory optimization are not violated. And we call this, we'll call this the time optimal reference trajectory. We visualize the data that is collected on the right. So some of the desired goals are highlighted in this black circles. The rest of the plotted states are the states that are achieved by the aerial vehicle while tracking these optimized reference trajectories. For better context, we also color code the achieved states by the velocities, so you can get an idea of what the data looks like. Now, once we collect this data set, the next objective is to distill from this expert data the goal condition policy. States and goals for this policy are in the forms of positions, velocities, and orientations of the aerial vehicle. The policy would then output actions in the form of collective body thrust and body weights. Body thrust denotes the amount of thrust that is required for acceleration. This is normal to the body frame, and body weights is basically the angular velocities that you would command to the aerial vehicle. Following prior goal condition RL work, the policy would then optimize for a goal reward, which is basically obtained when it reaches the goal within a specified threshold. So this is a sparse reward task where you only get a reward of 1 when you reach the goal. We then use an off-the-shelf offline RL algorithm to optimize the goal condition policy. To basically optimize the goal condition policy. Furthermore, we also use some of the tricks in goal condition learning, for instance, hindsight relabeling, whereby the desired goal is relabeled with some of the goals that are achieved by the expert, so that we can alleviate some of the learning issues that arise from sparse reward learning tasks. Once we follow this setup, there's an added benefit. And in hindsight, this allows us to learn goal condition policies that not only reach those final desired goals, but also reach the intermediate goals that the expert achieves along a given trajectory in the data set. We evaluate the learning performance over 2 sets of tasks, that is reach desired and reach intermediate. In the reach desired tasks, we initialize the quarter at the origin, and we task it to reach one of the desired goals that we collect the expert data from. In the reach intermediate task, the aerial vehicle will be initialized along some arbitrary initial state that is achieved by the expert, and it will reach a mixture of future achieved goals along the same given trajectory or the desired goal for that trajectory. And we benchmark 4 different algorithms over here, and we observe that GCSL, which stands for Goal Condition Supervised Learning, had the best performance over all tasks, as compared to the other state-of-the-art algorithms such as CQL, which stands for Conservative Q Learning, TD3BC, which is Twin Deterministic Policy Gradient with Behavior Cloning, and things like that. We also visualize some of the trajectories for each of these tasks. So the trajectories in blue are the trajectories that are resulting from executing this goal condition policy when the aerial vehicle is initialized from this green point and tasked to reach the red point, which is the goal. The orange trajectory over here is the expert reference trajectory that we basically obtain from the optimization process that I discussed for data collection. And you notice that the goal condition policy can execute trajectories that are almost close to the reference trajectory without even having access to this reference trajectory. We also conduct some more experiments leveraging this learned skill policy to reach goals that are not present in the dataset. So more formally, what we want to do is we want to plan a sequence of goals that the aerial vehicle can reach based on its training data to reach this final goal G, which is not in the training data set, from an initial state S0, let's say. In these experiments, we compile a set of 250 test goals with a position offset to 2.5 meters to 3 meters, and the velocities and accelerations are bounded by 2.5 meters per second and 5 meters per second squared. And for simplicity, the planning objective is just to optimize for a single intermediate goal. The planner then uses the value functions that are distilled during this goal condition policy learning phase, and these value functions basically indicate the reachability of the goal from a state. When you task a vanilla goal condition policy to reach these goals without the planner, it fails in all cases, as you can see in the results over here. With the planner, we observe some limited improvement in terms of reaching these out of distribution goals, albeit it's not spectacular. We also look at some of the qualitative visualizations of the trajectory for some of the successes. So here you can see that we can plan an intermediate goal for a goal condition policy to reach prior to moving to the red goal. Once the aerial vehicle reaches this green goal, then we change the goal for the goal condition policy and we task it to reach the red goal. And in some of these cases, it was able to reach the red goal without having any online fine-tuning or collecting any additional data. And with these results, I come to the end of the second half of my presentation. And some of the key contributions in this project are basically developing this data collection pipeline and learning pipeline to distill primitives in the form of this goal condition policy. We also show that the policy can be tasked to reach goals at a final grain resolution, as shown in some of the evaluations on single goal reaching tasks, that is the reach desired and the reach intermediate tasks. We also demonstrate the ability of leveraging the learned skills to plan towards reaching towards further goals, albeit there is still some room for improvement over there, more specifically 80% room for improvement. Here, basically one of the reasons why the planner fails to learn to plan towards out of distribution goals is a lack of coverage of data. And this could be a potential for future work where future work can be focused on collecting data autonomously and querying additional data from the simulator based on the needs of the task. Another line of work is to essentially use a higher level goal selection policy instead of doing a sophisticated planner-based method, which optimizes for the sequence of goals through a learned value function to prevent some of the biases that you encounter in learning the learned value functions from propagating into the planning phase. And this brings me to the end of my presentation. I'm grateful for your time. I'm open to any feedback and questions. Thank you.
Let's thank Harsh for a great presentation. Do we have any questions from the audience? Okay, so I get to monopolize the Q&A. I have two questions. In the first half, right, in the semantic part, did you have like more than one, when you're doing the semantic search, like, do you have more than one thing that you were searching for, or was it, okay.
Yeah, so we have more than one thing. So the red, the maroon, and the green are three different semantic categories of targets that you want to search for. And then each of these semantic targets is initialized with a prior. And then you basically like update the prior based on like individual sensing. We assume that there's a camera which has some percentage detection of some accuracy for detecting each of these semantics.
Okay. And so if you had new semantics, then I'm assuming that you have to that has to be somehow retrained.
If you have more layers of semantics, for instance, if there are like 7 or 8 semantics, then you want to retrain the policy.
Okay. So in the second half of your presentation, So the objective, right, is really the fact that you wanted to have a better, you wanted to get better quality trajectories compared to the motion primitive type, right, sort of trajectories that you normally get. And so the question is, how come, doesn't it make more sense to do like a trajectory, like a resulting quality type comparison between the sort of the trajectories you get from your learn policy versus the motion primitives? And and in that case, obviously we have to agree upon what we considered good quality versus bad quality trajectories, right? Do you have any thoughts on that?
Well, for this, I did not consider the case of just using the motion primitives to plan towards, like for instance, like this second task where we want to reach this final goal, out of distribution final goal. And I think it would be like useful to compare this with respect to a motion primitive based framework. But for this task, I didn't really have access to motion primitives as such, because those were the primitives in the first set of tasks are pretty much hand engineered. So yeah, I didn't have it for this task.
Okay. It's an interesting question, right? In the sense of like, to some degree, right, one could potentially argue that your motion primitives, though, yes, they're somewhat hand design, right? There's a very clear sort of design process, right? And it's very much first principles based, right? And obviously it's going to, because you're concatenating trajectories, obviously you are sacrificing some degree of quality based on that.
That's correct.
It would be interesting to be able to do that kind of a comparison.
Qualitative analysis.
Right. And mostly because, there's a cost to doing these learning based things, like you pointed out, and the need to, get training data and all of that stuff. Right.
That's correct.
And so I think it would be an interesting
comparison.
Comparison, because then at least you can say, well, do you spend, what are the length of the trajectories, right? What are what are the energy efficiencies, or that of one set of trajectories versus another? And I think that actually would make a really nice analysis in terms of what the trade-offs potentially are. But that's a really nice piece of work.